Review of all the things that are kind of happening in Unit 5. We did these in class, but for those who missed it and want to get caught up, of course, these are, you can scan forward and find things that you need to look at more carefully. So I wanted to talk through some of the other details that are on this as well as go through the things we've already done. Like the first question says polynomial or exponential. It's just to give you an idea of which one's which. And so in case you're wondering, the one on the right is a polynomial. And a polynomial is anything where you have x to a power as your terms, one or more terms, versus an exponential is when you take some number to the x, and so these are exponential. So when we talk about those types of functions, exponential means x is actually in the exponent. Then we get into this idea of graphing these, of course, and then doing growth or decay. Now, generally speaking, what we're going to look for is it's a growth if this number inside here is both positive and greater than 1, okay, in its value, and that'll make it grow. Because exponential functions repeatedly multiply by this number. So like when you have base 2, like that means whatever x you put in there, so let's say x is 2, you're taking 2 to the second power, which is 2 times 2, or 2 to the fifth power. It means 2 times 2 times 2 times 2. It's repeated multiplication of that particular number, and if it's a bigger than 1 number, it's going to keep growing. On the flip side of the coin, you'll have a decay if what's being exponentiated is a fraction, something less than 1. Now this one in the picture here is kind of hard to tell if you recognize the transformation that this is facing. It's got a horizontal flip in it. That's one way to notice this is a decay function. But I think the nice way to think about it is if you think of this as, instead of 3 to the negative x, you can think of it as 3 to the negative 1 to the x, and then you might remember, oh wait, that's 1/3 the x. So really this whole function is kind of like graphing 1/3 to the x plus 2. It will decay because ultimately that number that's being exponentiated or multiplied again and again is a number that is between 0 and 1. And that's whenever your factor is between 0 and 1, a fraction, then you know it's going to decay, repeatedly multiplying by a number less than 1, which chops it down by that factor each time. Okay, back to graphing those and some other details. Sorry for the speed of this. 1, because we did it in class. 2, because it's kind of review material. And 3, you have the pause button and rewind. So when you're watching videos, always stop and rewind as you like. I'm going to build it with a table and my knowledge of transformations. So when I look at this function, I'm going to, in the beginning, go, oh, look at that 1/4. That's a 1/4 vertical shrink. So I know that this graph is compressed vertically. I have a sense of what a 2 to the x graph looks like. So in my mind, I'm thinking of this growing function. So as I plot points, keep those ideas in mind. So for the first one, if I put 0 in, you're doing 1/4 of 2 to the 0. So I'm actually going to write these in here because I can with my handy-dandy little screen here. But 1/4 2 to the 0 is a 4th times 1. 2 to the 0 is 1, so it's just a 4th. So at the point when I put in 0, I get out a 4th is my first point, and I plot it on my grid. And then pick nice numbers. I mean, you're going to have to do all of these, and you can hopefully fill in that table. I don't know if you'll need them all, but it's helpful to have as many as possible. 2 to the first, of course, is 2. 2 times a 4th is actually 1/2. So when I plugged in 1, I got out a half. So plotting the point 1, 1/2, and onward and upward. So if I do the next one, 2, I'm just going up the scale. I don't always go up the scale like this, but for this one, it's easy enough. 2 to the second. You get out 4. 4 times a 4th is actually 1. So finally at 2 I get to 1. This is probably enough for me because I know what exponentials do. I know they have a horizontal asymptote. Really important to keep that in mind. That's part of the function. So that when I graph this thing, I'm just snuggling against that asymptote, hitting my 3 points, and then just kind of hitting an arrow at the end to make sure I got the rest of it. That's sufficient. That's fine. And then once the picture's in hand, then you can say, all right, domain, what possible x's do we have? All real, of course. What range do we have? Its lowest is 0, highest is infinity, and you make sure you put parenthesis around 0 because it does not touch it. That's an asymptote there. And the horizontal asymptote y equals 0. Let's be careful about using y equals for horizontal. When we get to vertical on the log graphs, we'll use x equals. Okay, to the next graph. Sorry again, we're going fast just to keep things going for some of you. I'll put in some numbers already. You can decide which one you want to look at. Do you want to look at the original or do you want to look at this modified version? They're both fine. If I put in some nice numbers, 0 always tends to work out pretty well. Plus it also gives, 0 is kind of like your if your input is time or x is time. We like it because we think of it as our initial value, what we start at time 0. So if I put in 0 in this one, I'm going to use the second one. A third to the 0 power is just 1. Add 2 to that and you get 2. So 0, 2 is my first intersection on that one. So the other thing I know about taking that graph to the next level, and I think I just added wrong. 1 plus 2 is 3, right? Pardon, while I write that thing in there. Anything to the 0 is 1, 1 plus 2 is 3, and I plotted it in the wrong point and everything. So, yeah, you know, sometimes we think through it better than we say it. Okay, there you go. Hopefully that's good. Then you put in any other number that you think is suitable. If I put in 1, it's not my favorite, but I actually get 1/3 to the 1, which is 1/3, and I get 2 1/3. That's okay. Those are nice. You're not doing perfect graphing, but 1, 2 and 1/3. Bingo. You can put in anything else. I might jump to 3 on this next one, or maybe even 2. It's up to you, but you can decide. It doesn't have to be in order. Just pick numbers you think will be helpful in graphing this graph that even in my mind now, I kind of know what I'm going to be doing. There's some kind of asymptote in there. So looking at that graph thinking, all right, it's downhill. Does it hit my asymptote? Ooh, I don't think it does. I think there's something wrong with that graph. So you want to keep your mind about you. When I put in 2, I get 1/3 squared and then add 2 to that. So that'd be 2 1/9. So it gets a little, oops, use the wrong pen. So 2 1/9. Bingo. And it seems to be just getting shorter and shorter and shorter. So when I put in 2, I get 2 1/9. And as you keep going, that 1/3 gets to a higher power. So if you think the next one would be 1 over 1/3 to the 3rd power, which is 1/27th, you put in 3, it just gets closer and closer to something. And we all know, if we've looked at our transformations, this exponential graph is up 2, which means my horizontal asymptote went from being y equals 0 to being y equals 2. And that's really important to know because that's where my graph will snuggle up against there. Now, if you want to put in one more, I would put in -1 because that's interesting. I would like to know what the graph is doing at x equals -1. I haven't plotted a point there, but if I do, I get 1/3 to the -1 and then add 2. Well, 1/3 to the -1 is actually 3 because you flip it over. You add 2, you get 5. So that's actually a much more interesting number. Sorry, 3 plus 2 and I get 5. I think I'm off the charts here. Okay, -1, 5. It does go off the graph, but it's nice to know -1, 2, 3, 4. Oh, it's right at the tip. 5. That'll help you finish off your graph. Knowing the basic transformations and shape is square one, and then from there, plotting points to fit that mold and being able to check your results is really important. Okay, going down to the domain, all reals are fine. You can put in any input you want. Range, though, starts at 2, goes on up, because remember, we vertically shifted it by 2. Doesn't touch 2, it's an asymptote, which means I need to write y equals 2 as my horizontal asymptote. Okay, the next ones are logs, and their transformations are a little bit trickier. So we want to keep that, it's not, I should say, trickier. You just have to know when you're graphing this, there's an easy way to do it. If we take advantage of our knowledge of some basic log base 3 values. That's log base 3 is something I know something about. Like I know what log base 3 of 3 is. I know it's 1. Log base 3 of 1, 3. Remember the question is 3 to what power equals the number inside. So 3 to what power is 1? 3 to the 0 power. Log base 3 of 9. But 3 to what power is 9? 3 to the 2nd power. So as I'm thinking of inputs for my x, these purple highlighted numbers, those are the things I'll choose for my x so that it's easy to plot. So when x equals 3, I got out 1. When x equals 1, I got out 0. When I put in 9 for x, I got out 2. And those are all points I can plot. Over 3 up 1, 1, 0, 9, 2. 9's off the charts, but it's kind of off in the distance here. I'll just kind of plot a point off to the side. But I put that too high. Here, I'll undo that real fast. 9, 2 be somewhere out there like that. Now, you guys know what a log graph looks like in general, so I'll just put the shape up there. You know there's a vertical asymptote at x equals 0, and then it takes off like that little purple highlight does. I'm going to be more precise when I do it this time, but your basic graph has to follow the properties that you know and love. Like, hey, I know all log graphs have a vertical asymptote, x equals 0 if they're not transformed to the left or right. And then I got these 3 points, so if, as long as I snuggle my graph up against that asymptote and hit these 3 points, or 2 is fine. If I get out there and actually hit that one at 2, 9, there's a rough sketch. That's good enough. It's actually pretty precise. But there you go. So pick nice numbers. Same thing for the next one. I'm thinking the same thing. The only problem is if I want to get those same nice numbers, instead of picking 3, 1, and 9 respectively, I'm going to actually pick like 4, because when I put 4 in there, that makes the log base 3 of 3, and so on. So because of that -1, I have to pick a little bit differently. So I'm going to put these each over here. I'm going to pick x equals 4, for instance, because -1, I get log base 3 of, so when I put in 4 for x, I get 4 minus 1, so log base 3 of 3, and then I add 2 to it. Okay, so, and the key is log base 3 of 3. You know that's 1. 2 times 1 is 2 plus 2, and I output 4 on top of that. And again, just pick a couple more that make your life easy. Instead of 9, I pick 10, for instance. But if you think about putting in 10 as your x, you're getting pretty far off the chart. So maybe I'll take that back. Maybe I'll try something else. Maybe I'll do, remember taking it of 1 is a good one. So if I put x equals 2 in there, so 2 log, and if I put x equals 2, I actually end up doing log base 3 of 1, which I know is 0. And I add 2 to that, and I get 2. So I can put the point 2, 2. 2, 2, 4, 4. Good points. I know what log graphs look like in general. I just know mine got shifted left 1, or I'm sorry, right 1 and up 2. So I just know I need to move this graph over right 1 and up 2. So I kind of realize, and I vertically stretch it a little bit as well. So I kind of have a sense of where this is going to be. Now, things that you want to always move with a log graph is take note of its asymptote. When I moved it to the right 1, I also moved the asymptote off of x equals 0 to being x equals 1. So that kind of helps. Now you see those 2 points that I plotted already? You can get a sense that, ooh, that graph's going to snuggle up against that asymptote. I'm going to pick another number here that's actually kind of nice, and you tell me why it's nice. I pick, let's see, I want to get 1/3 in there. I think that'd be kind of fun. Or even, actually, let's just do another one. Didn't I put 2 in there? I put 2, and I got that one out there. What if, I like that number. I'm going to put 2/3 in here. See what you think about that. So if I put 2/3, I'm sorry, oh, hey, off the charts. If I put it in there. If I put 2/3 in there, if you can imagine 2/3 minus 1, you're going to have an issue with putting 2/3 in for x in that original. I have some really splotchy shots here. 2/3 minus 1 gets you a negative number, and you'll get an error message. You can't calculate it because I've gone to the left of my domain, and those numbers are illegal over there. So when you pick this, you got to make sure the numbers you pick also are things you can plug in. They have to be bigger than 1. So I think I'm actually going to, let's do something else. I'm going to put in 4/3 this time, and that ought to be a cool number. You may not choose this, and you probably already have a nice sketch, and that's fine. But look what 4/3 does. This is pretty cool. Log base 3 and 4/3 minus 1. Think of it as 1 1/3. So you end up with 1/3 left times that plus 2. This little dude right here, log base 3 of 1/3 is -1. Okay, so this guy right here is -1 times 2 is -2 plus 2. I get out 0. And so what happens at 4/3, you get out 0, which is that intercept right there. And that might help you get that graph off the ground. I've graphed more than necessary, but that's kind of neat to show you the properties of graphing those logs. And good enough for this first video.